All right, buckaroos and buckarettes, here we go. We're talking about practice problems in Chapter 8. Miss Taylor, are you with us? Miss Taylor, can you hear me? Are you still awake? All right, so we look at this first one right here. And this solid, we're not going to talk about a whole lot about these conditions right here, right now. But what we're talking about, this is telling you that this is pure calcium, boom, is combining with pure sulfur. In this case, it's kind of strange. The sulfur's in this fluorette form where it's 8 atoms together. And we produce the calcium sulfide. Now, the key, obviously, is do you know the formula for calcium sulfide? Okay? It's the calcium. What the understanding is, calcium's a group 2 metal. It forms a 2 plus ion. Sulfide, when it forms an ion, is 2 negative. So it's a 1-to-1 ratio. Okay, so we form the compound, and now we've got the obligation to balance the equation. We've only got 1 sulfur over here, and we have 8 over here. So to balance this thing, first thing we're going to try is we put the 8 there. That gives us the sulfurs are balanced. Now we've thrown the calciums out of whack, so we got to put the 8 over there. And it is that easy, folks. The key to balancing chemical equations is understanding that there is no key. Okay? It's essentially trial and error. Now it helps a lot to be really good at writing chemical formulas. There are also some tips that you want to go to. For instance, you look for the subscripts, okay? You balance the water and the waters and the hydrogen, the oxygens last. Leave them till the end, okay? Particularly if the water comes apart, okay? If it comes into hydroxides and hydrogens, okay? A few little tips like that. But essentially, it's practice. And the more you practice, the better you get at it. Now, we're going to jump ahead a little bit here and talk about what type of reaction this is. There are 5 basic types of reactions that you're expected to know, and one of them is synthesis. And synthesis means you have 2 reactants, reactant, and you produce 1 product. In other words, a bond forms between the reactants. That's a synthesis reaction, sometimes called combination. So what is this right here? What type of reaction is this? This is a synthesis. Okay? Synthesis, and sometimes you'll see it referred to, and I think our book might even refer to it as a combination reaction. But you certainly shouldn't be stumped by either one of those terms, right? I forget how the state test asks you, but it's going to be combination or synthesis, okay? Synthesis is when you have multiple reactants and you form a fewer number of products. In other words, bonds are formed, okay? Now, if we took this baby and turned it around backwards, so we got these 2 atoms bonded together, we do something to it, add heat or whatever we're going to do to it, and we end up with 2 products, then that would be the opposite, and that would be decomposition. Okay? So those are 2 types, okay? So what type, so we go down here and we look at this one right here, and the key to this reaction, again, this is very simple to balance it. But the key is, any mistakes in here will be people forgetting that you have to write these as diatomic elements. Yes? Okay? So we know, everybody knows, I hope, that when hydrogen bonds, it's only got the 1 valence electron that it's going to play with. It's either going to bond by giving it up, or it's going to bond by sharing that 1 electron, okay? In this case, we're right on the verge of being ionic. But it's a 1-to-1 ratio with fluorine. Fluorine has 7 electrons, wants to take 1. Hydrogen conveniently has 1, right? So on. So this is a 1-to-1 ratio. Everybody should know that the hydrogen fluoride is 1 hydrogen and 1 fluorine, right? However, because these are have to be written as diatomic elements, you only produce this hydrogen fluoride in 2s, right? In order to balance the equation. 2 hydrogens, 2 hydrogens, 2 fluorines, 2 fluorines. What kind of reaction is that? Synthesis. Okay? Yes, what's the question? S. Now, you had a question? This is a 2. That's a 2, and this is a G for gas. Okay? You need to read the equation in the textbook, okay? Remember, I'm writing with it's a radioactive pen here, and I will probably die from handling this thing, you know, sacrificing my life to illustrate the finer points of chemistry by handling this pen, okay? And so sometimes it's difficult. A normal man probably wouldn't be able to hold this pen, okay? Now, here, and again, remember, I'm kind of cheating here by already setting these things up for you. This thing is asking you to take the word equation and put it into this form, right? All I've done, I've written the whole equation out here for you. I just haven't balanced it, right? And when we're going to go down the road, and it's not going to be long, we're going to go down the road, and you're going to be asked a question like this. And it's going to say in word equation, it's going to say solid aluminum is dropped into aqueous zinc chloride, 50-some grams of aluminum, 55.26 grams of aluminum, for example, is dropped into aqueous zinc chloride. Calculate the mass of the precipitate, right? In other words, this is going to get more complicated very rapidly. Okay? So you need to pay attention here and try to pick up on what we're doing, all right? So here we're told that solid aluminum is going to be dropped into aqueous zinc chloride, and we're going to end up with aluminum chloride and solid zinc. Now here's where your little states are very important that you understand, okay? This aqueous zinc chloride is telling you that we have zinc in a water solution, right? And the aqueous means it's dissolved, which means that it has dissociated into its ions. The ions from zinc chloride are 1 zinc ion with a 2+ charge and 2 chloride ions with each with a 1 negative charge, right? Okay. Now, the fact that it's in solution, it means it is distributed throughout that water solvent solution, right? Equally, 100% homogeneous. And the reason is because of the Brownian motion of the water molecules. The water molecules in the liquid state are moving very, very rapidly, and they are polar. The oxygen end is negative, the hydrogen end is positive, and so they are attracted to both the zinc and the chlorides, right? They're moving very rapidly, and so that motion and that kinetic energy is what puts those electrons, there's the oxygen, okay, and we say use this as delta H here, and the hydrogens are here, and that's what keeps those particles, in this case the particles are the ions, the zinc and the chloride ions, it keeps those particles in solution. So this end is positive compared to this end, which is negative, and the reason is these two polar bonds here, okay? And the center of the positive region is down here. And this is something very important we're going to go in the very near future. It's like 3 chapters on solutions only. And the reason that the water dissolves these substances is because the water and the substances are polar. If they weren't polar, they wouldn't dissolve in water. Now, someone asked me for an example of one where it's not polar. Well, I'm going to pretend like you asked, and I'm going to say thank you, okay? Let me give you an example. Right here in this equation, okay? So here we have the picture where we've got this zinc chloride in aqueous solution, which means the zinc ions and the chloride ions are floating around, yes? Okay? We put the aluminum in there, and what we need to understand is that the aluminum is more reactive than the zinc. What does that mean for metals? It means the aluminum forces its electrons onto the zinc ions. How do we know, Kimosabe, that that's going to happen? We turn to page 286. It's called the activity series of metals. That would be your cue to turn to page 286. That would be your cue to turn to page 286 and look at the activity series of metals. And what that shows you is that every metal, you see that list of metals in a column, right? Every metal that is lower than any other metal is less reactive. In other words, the higher the metal is in the activity series, the more reactive it is. You see that aluminum is above zinc, yes? That means aluminum will displace zinc in this equation. Now take, for example, if we turned it around and we had aluminum chloride and we dropped some zinc in it, what would happen? We designate that with an NR, no reaction. There would be no reaction. How do you know that? Because zinc is below aluminum. Zinc cannot force its electrons onto the aluminum ion, right? The aluminum forces its electrons onto the zinc ion. Here's a very important chemistry lesson. As soon as the two aluminums, each giving up 3 electrons, right? That's a total of 6 electrons. Give them to 3 zincs, each accepting 2 electrons, right? The zincs lose their +2 charge and become 0, right? No longer polar. What happens to them? Look at the equation. They fall out of solution. They go to the bottom of the beaker. That's an example of nonpolar substance not dissolving in a polar solvent. Water is the polar solvent. It only dissolves polar solutes. And the ultimate polar solute are these ions. Okay? So as soon as the zinc loses its charge, boom, falls out. As a matter of fact, when you got that solution of water and zinc chloride dissolved, right? The zinc chloride is in aqueous solution, and you take that little piece of aluminum and drop it in there, what happens? It drops to the bottom like a rock. But if you observed it over time, what you'd see is that the aluminum is slowly, the sample of aluminum is slowly getting smaller, and you'll notice this substance forming on the bottom of the beaker. What is the substance coming out on the bottom of the beaker? It's the zinc falling out of solution. What happens to the chlorine? The chloride ions? Nothing. They were negative ions when you started. They're negative ions when you finish. They stay in solution. Got it? Very, very important. There's a ton of chemistry in that discussion right there, okay? You try to hang on to it. Yes? So we haven't even started talking about balancing the equation yet. What we're talking about in balancing the equation is this. The aluminum bonds with chlorine only in a 1:3 ratio. The zinc bonds with chlorine only in a 1:2 ratio. So the crux of the problem in balancing this equation is obviously the chlorine, right? So it's very simple. You can't change the subscript. You don't balance equations by changing the subscript. Those are set in stone, okay? So what you have to do is manipulate the coefficients in such a way that you balance out the number of atoms. In this case, it's as simple as finding a common denominator between 2 and 3. What is it? 6. So you put 2 here, that gives you 6 chlorides. You put 3 here, that gives you 6 chlorides. Okay? So now you've balanced the chlorides, but you've fouled up the relationship between zinc and aluminum, right? So now you got to go back and straighten that out. You've got 3 zincs here and 1 here, so what are you going to do? Put a 3. You've got 2 aluminums here and 1 here, so what do? Put a 2. Okay? Now, double check. Make sure that this is a smallest whole number ratio, 2, 3, 2, 3, and it is. Can't reduce that any further, right? It's a balanced chemical equation. Now, another point I need to make here. You see this zinc listed as the solid. That tells you that it is not an ion anymore. And you need to know, what you need to know is, if it's not an ion, it's not charged, and it's not going to be soluble in water. Unless it's less dense, right? Okay? And then the other thing you could do is write this with a down arrow, and that means it precipitates. That means it precipitates out. So you would never write these two together, one or the other. Okay? Everybody has it? Yes? Hello? All right, so now what we need to do is flip the page to what is it? We're on 68, 272, I believe, and let's work on those. Okay? Work on those for a second, and I'll come